fourth problem. So here in the fourth problem, once again I need to find out the extension in the bar which is suspended freely. Once again, it's a uniform bar which is suspended freely, that is fixed at one end, and this is the bar which is having a length L. This is the bar which is having a length L, and this is the axis of the bar. Now, what I need to find out here, I need to find out the extension in this bar. Say, let us say this is the extension because of its self weight. I am not applying any force here. When it is suspended against the gravity, there will be an extension due to the depends on the density of this material. So I need to find out what is the extension. This extension because of its own weight or self weight. Once again, we can consider this bar is having an Young's modulus E, area A. Now I'll consider the density rho. Okay. So extension now we don't have any force here. If it is force applied, there will be an extension. But here extension is because of the gravity. So that extension I need to find out using Rayleigh-Ritz method. Once again, I have to use Rayleigh-Ritz method and I have to find out what is the extension in this bar. So this extension I have to find out. Now how to find out? Same way. First one is you need to formulate the P function. You have to formulate the P. So my pi is equal to, it is strain energy plus work potential. Once again, it's a bar. Therefore, my strain energy will be equal to EA divided by 2 integration over the length L. It is du by dx whole square into dx. So this is strain energy as it is a bar. It is fixed. Only now work potential changes here. Now once again, let us consider a small element here. Let us consider a small element which is having a length dx. I'll consider a small element which is having a length dx. Now, can you tell me what is the work potential for this element? What I have considered? It is force into displacement. So let us consider once again displacement. Uh, as we know, the displacement at the fixed end is 0, and here I have a maximum displacement. Correct? No, at the free end. So similarly, the displacement at any random distance, I don't know, that I am going to consider it as an u. So to get the work potential, what is required? I need force into displacement. Work potential is nothing but something like work. So what is work? It is force into displacement. So displacement, where I have considered, see, when I am doing for the element, I have to consider the displacement at the element. So let us consider the displacement at the element is u. So I know this displacement u. Only thing is I need to find out the force. Now that force is what? Now that force is because of whatever the density of the material. So how I can write that? It is A into rho into dx. So this is my force. How it is A into rho into dx? What is my area into dx? What is my area into dx? What I'll get if I multiply area into dx? What is dx? Dx is my length of the element. Nothing but it is area into length. If I multiply area into length, what I am going to get? I am writing here area into length. The volume. So density is what? Weight by volume. Density is weight by volume. So this volume will be get cancelled, left with weight. So nothing but it is the force. So this entire term what I have written here, this is my force. So that force multiplied by displacement will give you the work potential. Now this is the work potential for the element. Now I want work potential for the entire part. So it is 0 to L. So A into rho into U into dx. So this is what my work potential for the entire bar. Now you know the strain energy. This is my equation number 1 and this is my equation number 2, and this work potential is what my equation number 3. Now you have to substitute the equation number 2 and 3 in equation number 1 to formulate the PE function. Therefore pi is equal to it is EA divided by 2 integration 0 to L du by dx, that is my strain whole square into dx minus, so as I told, work potential it is always negative. So it is minus integration 0 to L, it is A into rho into U into dx. Okay. So this is my entire P function I have formulated. Now in the next step, what you can do, you can consider the trial displacement function with the same second order polynomial function. Then here area and density are constant. That two things you can take it outside. U is what? Same thing you are going to get. U is equal to, it is a1 into x plus a2 into x square. That is what my u. Whereas u1 is a1 into l plus a2 into l square. So after considering a polynomial function of second order and putting the boundary condition, I am going to get these two equation. So this you can substitute here, and similarly this you also you can substitute here after taking this a into rho outside the integration. Then further simplification. So same thing here, whatever the simplification you have done in the previous problem, this first portion is same. Only there is a changes here. So you have to different. I mean integrate it with respect to x. Put the limit 0 to l. Further you simplify. Then you will get a simplified p function. So that simplified p function you minimize it by differentiating with respect to a1 and a2. Equate it to 0. You will get two equilibrium equations. Solve those two equilibrium equations to get the constants of a1 and a2. Then substitute those values of a1 and a2 in u1 equation, so that you'll get the extension in the bar due to the self weight. This you can take it as a homework. Okay, so you try to solve. Anyhow, the first portion of this p function simplification is same what you have done in last three problems, but only there is a change here in the work potential, so that you carefully simplify it, minimize it. Then after minimizing, what you can do is get the values of a1 and a2, substitute those values of a1 and a2 into this equation to get u1. When you solve, whether you obtained correct or not, for that I'll give the values of a2, a1 as well as the final extension. So the value of a2, what you are going to get it is minus rho divided by 2e. This is the value of a2. Then value of a1. The value of a1 is rho into l divided by e. This is positive, this is negative. So these are the values of a2 and a1. Please note down. Then similarly, I'll give the value of u1. So after substituting this value of a2 and a1 in this u1 equation, after simplification, you'll get the value of u1 as it is rho into l square, divided by 2e, rho into l square divided by 2e. So this is my final expression. So you just try do simplification and try to get the a2 a1 value. Compare whether you have obtained the same value or not. If you are not getting this same value, you cross verify, somewhere you will be gone wrong. Check that and get these two values, substitute into this equation and get the final. The same expression is there using mechanics of material also. You just go through any book of mechanics of material, there you will get the extension due to the self weight of the bar. You have same expression. How you obtained delta L is equal to PL divided by AE for uniform bar when it is subjected to an axial force. In this case also you obtained U1 is equal to PL divided by AE. Similarly, the extension due to the self weight of the bar, this is the same equation which is there in mechanics of metal, and using RR method also we have obtained the same equation. You can cross verify that equation also. You refer any of the mechanics of metal book, you will get the same expression. Okay, so these are the four problems which are related to the bar.
Okay, guys, in next class, we will continue with beam problems using RR method. So thank you for watching. Please like, comment, and subscribe the channel.